There is a moment that happens in the life of every great explorer, somewhere deep in the journey, when the question of returning home stops being a logistical problem and becomes something else entirely. Something heavier. Something that doesn't have a clean answer. For centuries, sailors who left for distant shores understood that the ocean crossing back was never guaranteed. For the mountaineers who pressed toward the highest points on Earth, there were always those who understood, before they took a single step upward, that the descent was its own kind of reckoning. The way there and the way back are never the same journey, but none of them faced what the first humans on Mars will face, because the first humans on Mars will not simply be far from home in the way that explorers have always been far from home. They will be separated from Earth by something that no distance on this planet has ever truly prepared us for. A gap so vast, so unyielding, and so indifferent to human need that the word return may carry a different meaning entirely by the time they arrive. And here is the thing that tends to get lost in the excitement of mission planning, in the breathtaking imagery of rocket launches, in the carefully worded press releases about the future of humanity among the stars. The question of whether those first humans can come back is not primarily a question of fuel. It is not primarily a question of rocket technology. It is not primarily a question of money. It is a question that cuts far deeper than any of those things. It reaches into the biology of the human body, into the psychology of isolation, into the physics of an alien world, into the hard mathematics of orbital mechanics, and into something that scientists and mission planners are only beginning to fully grapple with. The truth is that some of the most respected minds in space exploration have already begun to quietly accept something that the headlines have not yet caught up to, that for the first humans who set foot on Mars, the journey back may never happen. Not because something will go wrong, but because of everything that will inevitably go right. This is the story of why. Most people understand, in a rough and general way, that Mars is far. They know it is the fourth planet from the Sun. They know it has a reddish surface and thin air, and that rovers have been rolling across it for years. They know that people talk about going there, that space agencies and private companies have produced concept art and timelines, and carefully rehearsed enthusiasm. What most people don't fully feel is the distance, not the number. Numbers lose their meaning at a certain scale. The problem with numbers like 34 million miles is that the human brain has no reference point for them. 34 million miles is Mars at its closest approach to Earth, a configuration called opposition, which happens roughly every 26 months. It sounds manageable when you say it quickly. 34 million miles. Like a road trip that just takes a while. But consider what that distance actually means in terms of communication. When the Perseverance rover needs to send a signal back to mission controllers at the Jet Propulsion Laboratory in California, that signal travels at the speed of light, the fastest thing in the known universe. And at Mars's closest approach, that signal still takes approximately 3 minutes to arrive. At the farthest point in Mars's orbit relative to Earth, that same signal takes over 22 minutes. This means that if something goes wrong on Mars right now, you cannot simply call for help. You cannot have a real-time conversation with anyone on Earth. By the time your message arrives, and by the time the response travels back to you, at minimum 6 minutes have passed. At worst, 44 minutes. Every exchange, every question, every emergency. For the rovers, this has always been a manageable constraint. Rovers can be programmed to pause, to wait, to make conservative decisions while humans think. But for human beings, standing on the surface of another world, watching something go catastrophically wrong, that communication delay is not an inconvenience. It is a fundamental redefinition of what it means to be alone. The Apollo astronauts on the moon could speak with you in something close to real time. The moon is close enough that light takes only about 1¼ seconds to make the crossing. A brief pause in conversation, barely noticeable. The Earth hanging visibly in the lunar sky, enormous and blue, close enough to feel like a neighbor. Mars offers no such comfort. At Martian distances, Earth will be a bright star in the sky, not a world you can see with your naked eye in any meaningful detail. A point of light among other points of light, remarkable only because you know what it is, and the conversations you can have with the people on that distant star will be structured more like letters than like phone calls. You send a message, you wait, you receive a reply, you wait again. This is the first thing that most mission timelines don't fully account for in the popular imagination. Not the technical challenge of communication delay, which engineers have thought about carefully, but what it does to a human being psychologically to stand on a world where help, in any meaningful and immediate sense, does not exist. And that psychological reality connects to something that researchers have been studying with increasing urgency. Something that has emerged from the most comprehensive long-duration space studies we have ever conducted. Something that has been quietly changing the conversation about what a Mars mission actually requires of its crew. But before we get there, we need to understand the journey itself, because the distance to Mars is not just a number to be crossed. It is an environment, an active, hostile, continuously damaging environment that the human body must survive simply to reach the destination. When NASA began studying what happens to astronauts on the International Space Station during 6-month and then 12-month missions, they discovered something that the early optimistic projections had underestimated. Space is not merely difficult to survive. Space actively remakes the human body. The process begins within the first few days of leaving Earth's gravity. Fluid that gravity normally keeps pulled toward your lower body begins redistributing upward. Astronauts describe the feeling as a constant mild head cold, a pressure in the sinuses, and behind the eyes that never fully goes away. The face puffs slightly. Vision changes in ways that took researchers years to fully understand. That last part is worth pausing on. Studies of astronauts returning from long-duration missions on the International Space Station revealed a phenomenon that had not been anticipated. A significant number of them experienced lasting changes to their vision. Some became more farsighted. Some reported blurred vision that persisted long after they returned to Earth. Researchers eventually connected this to a condition called spaceflight-associated neuroocular syndrome, in which the fluid pressure dynamics of the body in zero gravity cause the optic nerve sheath to expand and the eyeball to change shape slightly. The structure of the eye itself is altered by living without gravity. This is not a small finding. This is the body telling us, in very direct physical terms, that it was not designed for extended periods in space. And vision is only the beginning. Without the constant low-level resistance that gravity provides, bones begin losing density at a rate roughly 10 times faster than a person experiences during the bone loss of aging. Muscles atrophy. The cardiovascular system, which evolved to pump blood against a gravitational gradient, begins to change the thickness of its own walls. The immune system behaves differently. The gut microbiome shifts. Even gene expression changes, as studies of twin astronauts have demonstrated, with certain genes turning on or off in response to the space environment in ways that can take years to fully reverse after return to Earth. Now consider the journey to Mars. The minimum transit time for a one-way trip to Mars using current or near-future propulsion technology is approximately 7 to 9 months. This assumes a Hohmann transfer orbit, essentially a path that curves between the two planets at a moment when their positions in their respective orbits make the journey most fuel efficient. In practice, depending on launch windows and mission architecture, transit times of 6 to 8 months are commonly discussed as realistic targets. 6 to 8 months of zero gravity, 6 to 8 months of continuous radiation exposure, which we will return to in detail shortly. 6 to 8 months in a spacecraft smaller than most apartments, with a crew of perhaps 4 to 6 people, eating food that has been processed and packaged for long-term storage, breathing recycled air, exercising for hours each day in an attempt to slow the inevitable physical deterioration. And then, after all of that, you arrive. Not at Earth, not at a hospital, not at a recovery facility with medical staff and gravity therapy and fresh food and comfortable beds. You arrive at Mars, and immediately the work begins. It is easy to think of Mars in the abstract, a destination, a symbol, a stand-in for human ambition and the drive to explore. Concept art tends to show warm sunsets, dramatic rock formations, a certain geological grandeur. The rovers send back images that, if you squint at them in a particular way, almost resemble places on Earth. Certain deserts, high-altitude plains, the kind of terrain that looks difficult but not alien. The reality of Mars is considerably less forgiving. The atmosphere of Mars is roughly 1% the density of Earth's atmosphere at sea level. A human being standing on the surface of Mars without a pressurized suit would not simply find the air unbreathable. The air pressure itself would be insufficient to keep body fluids from boiling. The moisture in your lungs, in your eyes, in your blood would begin to vaporize. This process, which scientists describe as ebullism, is not quick and it is not peaceful. Mars is not a place where the environment is merely challenging. Mars is a place where the environment actively attempts to end you at every moment. Through multiple simultaneous mechanisms, the temperature on the Martian surface swings between extremes that would be unusual, even in Earth's most hostile environments. Near the equator, on a summer afternoon, temperatures can briefly reach just above freezing. But within a few hours, as night falls, the same location can drop to minus 60 or 70 degrees Celsius. Near the poles, temperatures plunge far below that. A human in even a well-insulated suit would need continuous active heating simply to survive. Then there is the dust. Martian dust is not like terrestrial dust. It is extremely fine, with particles small enough to penetrate almost any seal that isn't engineered to the highest specification. It coats solar panels, reducing their efficiency. It gets into mechanical systems. Studies of Martian soil have revealed that it contains perchlorates, chemical compounds that are toxic to humans, and that would, if inhaled or ingested in sufficient quantities, cause serious health problems. The dust also carries the residue of Mars's complex UV radiation environment, which has over billions of years created reactive chemical compounds at the surface. Every EVA, every extravehicular activity, every time an astronaut steps outside the habitat onto the Martian surface, brings these particles back in some form. And global dust storms on Mars are not rare events. They are periodic features of the Martian climate. During a global dust storm, which can last for weeks or months, and can cover the entire planet, sunlight reaching the surface is dramatically reduced. Temperatures drop, solar-powered systems are stressed. Anyone relying on solar energy for survival must have backup systems capable of sustaining life through an extended period of greatly reduced solar input. The Spirit rover was ultimately killed by a Martian dust storm. It ran out of power and never resumed contact with Earth. For a human crew, the equivalent scenario is not an equipment loss. It is a survival crisis. All of this is known. Mission planners have thought about it carefully, and there are engineering approaches to every individual challenge. Better power systems, better seals, better filtration, better habitat design. The problems are not individually unsolvable. What makes the Mars surface environment so significant for the question of return is not any single challenge, but the cumulative, unrelenting nature of all of them together. The crew arrives on Mars already physically diminished by months of space travel. They step out onto a surface that attacks their equipment, their health, and their psychology simultaneously. And they must perform extraordinary, physically demanding, intellectually intensive work under all of these conditions, for months, without any possibility of rapid evacuation, without any possibility of rapid resupply. And then, when the work is done, they must get back into a spacecraft. If the spacecraft is still there, if they are still physically capable of flying it, if the launch window still exists. This is a detail that tends to get smoothed over in popular accounts of Mars missions, because it is technically complex and it doesn't make for easy storytelling, but it is one of the most consequential constraints shaping the entire question of return. You cannot leave Mars whenever you want. The orbital mechanics of the inner solar system are precise and unforgiving. Earth and Mars orbit the Sun at different speeds and at different distances. Earth completes an orbit in roughly 365 days. Mars takes about 687. This means that the two planets are constantly changing their positions relative to each other, and the geometry of that relationship directly determines when a spacecraft can make the journey between them with a reasonable fuel expenditure. The windows when Earth and Mars are positioned for efficient transfer occur approximately every 26 months. Miss the window, and the next one is more than 2 years away. For a crewed Mars mission, the typical architecture that mission planners have worked with involves a stay on the Martian surface of somewhere between 300 and 500 days, specifically because this duration bridges the gap between the outbound launch window and the next available return window. This is not chosen because it's an ideal amount of time to spend on Mars. It's chosen because the physics of the solar system don't offer an alternative without an enormous and potentially prohibitive cost in additional propellant. In some mission architectures that have been proposed, particularly early conceptual work by engineers at NASA and at private companies, the surface stay might be compressed by using a faster trajectory. But faster trajectories require dramatically more fuel, which means more mass, which means more cost, which creates compounding engineering challenges throughout the entire mission design. The practical reality is this: the first humans to land on Mars will likely be committed to a surface stay of well over a year before any return becomes physically possible. Not because anyone wants them to stay that long, because the solar system requires it. And during that year and more on the surface, the crew will be experiencing something that no controlled study, no Antarctic isolation mission, no submarine deployment, no space station mission has ever fully replicated. They will be experiencing the most complete isolation from Earth that any human beings have ever endured. Not just physical isolation, not just communication delay, but a psychological reality that researchers who study long-duration space missions describe in terms that deserve careful attention. There is a concept in Antarctic exploration called the third quarter phenomenon. Researchers studying teams of people isolated in Antarctic stations through the long polar winter noticed that a reliable pattern emerged. The first stretch of isolation, while challenging, was often manageable. People focused on the novelty of the experience, on the tasks ahead, on the excitement of the mission. The final stretch, when return was clearly approaching, often showed a similar resilience. People drew energy from the proximity of home. It was the middle period, after the novelty had faded, and before the end was genuinely in sight, where psychological deterioration tended to accelerate. Interpersonal conflicts intensified, motivation faltered. Depression became more common. Cognitive performance sometimes declined in measurable ways. The third quarter phenomenon. Now consider a Mars mission. The crew launches from Earth with all the psychological fortification that training, preparation, and genuine excitement can provide. The first weeks of transit are novel, demanding. There is work to do, systems to monitor, an extraordinary experience unfolding around them. The novelty carries them. Then, somewhere in the middle of that 6 to 8 month journey through empty space, with Earth shrinking to a bright star behind them and Mars not yet visible as a disk ahead, the novelty fades. The crew is in a confined environment, roughly the size of a large recreational vehicle. They have seen the same faces, heard the same voices, navigated the same small spaces every day. For months, the same meals from the same food supply, the same exercise routines, the same carefully managed schedules. Russian space medicine researchers who have studied cosmonauts on long-duration International Space Station missions have documented patterns of psychological change that bear close attention. Irritability increases. Sleep quality declines. Interpersonal friction rises. The ability to manage conflict decreases at precisely the moment when the crew's proximity makes conflict most likely. These are not weak people. These are among the most psychologically resilient human beings ever selected, tested, and trained. They are chosen in part because of their exceptional ability to manage stress, to cooperate under pressure, to maintain performance in demanding circumstances. And still, months of isolation in a small spacecraft with no rescue possible begins to change them. Now extend that isolation through the surface mission. The crew arrives on Mars. They have been in space for months. They are physically diminished. They step onto a world that has never once in the history of its existence felt the footprint of a living thing. The scale of what they are doing is extraordinary, but they must work. The mission schedule is dense with activity because the time on the surface is precious and expensive. and the science program is structured to extract maximum value from every day. EVAs, sample collection, equipment maintenance, habitat monitoring, experiments, communications with Earth. The Earth that takes up to 22 minutes to respond to anything they say. The Earth that cannot, in any practical sense, tell them what to do in an emergency, because the emergency will have resolved itself, one way or another, long before the advice arrives. Psychological research on analog environments, including underwater habitat missions, isolated Antarctic stations, and simulated Mars missions conducted in remote environments, consistently shows a pattern. Human beings adapt to isolation. They develop strategies for coping with confinement and monotony and interpersonal friction. They survive it. But adaptation is not the same as thriving, and there is something specific to the Mars mission scenario that analog environments have not been able to fully simulate. The awareness that going home is not an option. In every Earth-based isolation study, in every Antarctic mission, in every submarine deployment, the participants know at some fundamental level that emergency evacuation is possible. The mechanisms are expensive and difficult and would represent a failure of the mission, but they exist. If someone has a medical emergency, if someone's mental health deteriorates beyond the ability to function, if something goes catastrophically wrong, there is, in principle, a way out. On Mars, during a surface mission, that awareness does not exist. If a crew member experiences a medical emergency requiring surgery, the surgery must be performed in the habitat by a colleague with medical training, and whatever equipment was included in the mission manifest. If a crew member's mental health deteriorates to the point where they pose a risk to themselves or to the mission, the crew must manage that situation with the resources they have. On a planet where evacuation to Earth is not a concept that applies, this is not a failure of planning. It is simply the nature of the distance, and it creates a psychological environment that has no precedent in human exploration. Because the explorers who came before, however far they traveled, however long they were gone, however difficult their journeys, always had one thing: the possibility of home. The first humans on Mars may not. In 2013, NASA published data from the Curiosity rover's radiation assessment detector, which had been measuring radiation levels during the transit to Mars and on the Martian surface. The findings were carefully worded, scientific, appropriate in their tone, and quietly alarming. The radiation environment beyond Earth's protective magnetic field and atmosphere is fundamentally different from anything human beings evolved to handle. The Earth's magnetosphere deflects a continuous stream of charged particles streaming from the sun, the solar wind, as well as higher energy particles arriving from outside the solar system entirely, galactic cosmic rays. The atmosphere adds another layer of shielding. The result is that people living on Earth's surface receive relatively modest radiation doses throughout their lifetimes. A crew traveling to Mars and back loses both of those protections simultaneously. The Curiosity data showed that the transit to Mars each way delivers a radiation dose roughly equivalent to the total career exposure limit that NASA currently allows for its astronauts. Just the transit, not the surface mission, not the return journey. Add the surface mission, where Mars's thin atmosphere provides only partial shielding, and where no global magnetic field exists to deflect the solar wind, and the cumulative radiation dose for a complete Mars mission round trip substantially exceeds what current safety guidelines consider acceptable. This has several implications. The increased cancer risk is real and measurable. Researchers have estimated that a Mars mission crew would face a meaningfully elevated lifetime risk of cancer compared to what their baseline risk would have been. The exact numbers are uncertain because the long-term biological effects of this kind of radiation exposure are not fully understood, particularly the effects of galactic cosmic rays, which are extremely high-energy particles capable of penetrating most conventional shielding materials and causing ionizing damage deep within tissue. But radiation does more than increase cancer risk. High doses of radiation affect the central nervous system. Studies in animal models, particularly rodents exposed to simulated galactic cosmic rays, have shown effects on cognition, on memory, on behavior. Changes in the brain's processing of information, increased anxiety-like behaviors, impaired performance on tasks requiring attention and memory. The relevance of these animal studies to human beings is actively debated, and researchers are careful not to draw direct conclusions. But the underlying physics is not in question. Galactic cosmic rays are capable of penetrating brain tissue. They deposit energy as they pass through. That energy causes damage at the cellular level that the body's repair mechanisms were not specifically optimized to address. For the first humans on Mars, this means that by the time they complete a round trip, they will have spent well over a year receiving radiation exposure that no human being in history has ever received on such a sustained basis. And they will have spent a significant portion of that time in a cognitively demanding, high-stakes, physically challenging environment. The question of how their minds and bodies will be functioning by the end of that journey is one that researchers can model, but cannot answer from direct human data because no such data exists. What we know from the animal models, from the long-duration station studies, from the physics, is that the concern is legitimate and significant, and it connects directly to the question of return, because return requires a functioning crew, a crew capable of flying a spacecraft, of making complex decisions under pressure, of performing the precisely timed sequence of actions required to launch from the Martian surface, transit back through interplanetary space, and return safely to Earth. If the radiation exposure over the course of a Mars mission meaningfully degrades cognitive function, degradation occurs at exactly the time when the crew most needs those functions to be intact. This is not a reason to abandon Mars exploration. It is a reason to take the return question more seriously than the popular narrative often does. Let us talk about the rocket. To leave Mars, you need one. This might seem obvious, even a little mundane, but the implications are extraordinary when you think them through carefully. Every mission to Mars requires that a return vehicle be either sent ahead of the crew or included in the crewed mission stack. In most mission architectures that have received serious engineering analysis, the Mars Ascent Vehicle, the rocket specifically designed to lift the crew from the Martian surface to an orbiting vehicle that will then take them back to Earth, is either pre-landed on Mars before the crew arrives or assembled on the surface. Pre-landing a rocket on Mars is itself an enormous challenge. Landing anything large on Mars is difficult. The atmosphere is thin enough that you cannot simply use parachutes the way you might land a capsule on Earth. It is dense enough that aerodynamic heating is a concern during entry. The combination of thin air and significant gravity means that the deceleration techniques that work in Earth's atmosphere don't scale easily to the masses required for a crewed mission. NASA's Mars landing systems have grown in sophistication over the decades. The Curiosity and Perseverance rovers used a remarkable sky crane system, lowering the rovers on cables from a hovering descent stage. But those rovers weighed roughly a metric ton. A Mars ascent vehicle capable of lifting a crew of 4 into orbit would need to carry far more mass to a much higher altitude. The engineering challenges are significant, solvable in principle, but requiring propellant that either needs to be brought from Earth at enormous expense or manufactured on Mars using a process called in situ resource utilization, essentially making fuel from the Martian atmosphere and soil. The Perseverance rover has already demonstrated one component of this on a small scale, using an instrument called MOXIE to convert Martian carbon dioxide into oxygen. It is a proof of concept for a process that would need to operate at orders of magnitude larger scale to produce the propellant a crewed ascent vehicle would require. Now here is the part that mission planners discuss in careful, measured language, but that tends to get softened in public-facing accounts. The Mars ascent vehicle, however it gets there, will have been sitting on the surface of Mars for a period of time before the crew arrives. Exposed to Martian dust storms, exposed to temperature swings of 100 degrees or more between day and night, exposed to perchlorates and to the chemical reactivity of the Martian's soil, operating in an environment that has proved capable of disabling or destroying equipment that was not expected to fail. The thermal protection system on the Opportunity rover, one of the most successful planetary science missions in history, outlasted its design lifetime by more than a factor of 10, but it also eventually ended. The environment of Mars is patient. It does not rush, but it works continuously on every surface, on every seal, on every component, with an indifference that no material can resist indefinitely. A Mars ascent vehicle that has been pre-landed would need to remain functional for the years that the crew is in transit and on the surface before it is used. Its propellant storage systems, its engine components, its avionics, its structural integrity, all of it must survive that extended exposure to one of the most equipment-hostile environments in the solar system. If the ascent vehicle fails, there is no backup option. There is no spare rocket somewhere on Mars. There is no way to send a replacement in time. The crew is on Mars, and this is the moment at which the question of return stops being theoretical. For most of the history of human spaceflight, the goal of return has been treated as non-negotiable. The Apollo program invested enormous resources in the lunar module's ascent stage, in the command module, in the entire elaborate architecture of getting 12 human beings to the moon and back. Because the idea that they would not come back was politically, morally, and psychologically unacceptable. But Mars is not the moon. And over the past decade, as mission architects have moved from conceptual enthusiasm to serious engineering analysis, a different kind of conversation has begun to emerge. Elon Musk, who has thought about Mars mission architecture with more engineering specificity than almost anyone outside of institutional space agencies, has been explicit about something that tends to provoke strong reactions when stated plainly. Early Mars settlers, in the vision that underlies SpaceX's approach to the mission, should be understood as people who are going to build a civilization on another planet, who may go knowing that they are unlikely to return, who are choosing Mars not as a destination to visit and leave, but as a place to inhabit. This is sometimes described as a colonial model, and it comes with serious ethical questions that we will examine shortly. But the engineering logic behind it is more straightforward than the emotional response to it. Building the infrastructure to return people from Mars is expensive, enormously expensive, in terms of mass that must be launched from Earth, in terms of the complexity of systems that must function reliably across multi-year timelines, in terms of the propellant requirements of the return journey. Every kilogram dedicated to return architecture is a kilogram not available for surface infrastructure, for science equipment, for life support redundancy, for the equipment needed to actually do anything productive on Mars. There is a mathematical argument that the first phase of Mars exploration is simply more achievable, more sustainable, and more likely to succeed if the return architecture requirement is relaxed or removed. Serious mission architects at NASA have also grappled with a version of this question, though they arrive at it from a different direction. NASA's Human Research Program, which studies the health risks of long-duration spaceflight, has identified return from Mars as one of the most challenging health and safety problems in human spaceflight history. The accumulated health risks of the transit, the surface mission, and the return journey are substantial enough that some researchers within that program have publicly stated that the acceptable risk for a human Mars mission may require the standards applied to exceptional exploration missions rather than normal operational spaceflight standards. What that means, in plain language, is that the people designing Mars missions recognize that the risk of serious health consequences, including permanent health consequences, cannot be reduced to the levels we currently consider acceptable for, say, an international space station mission. The first humans on Mars will be accepting a level of personal risk that has no parallel in any other chapter of human exploration. Not because the people planning these missions don't care about their crews, but because the physics, the biology, the engineering, and the economics of the situation make certain outcomes essentially unavoidable. Here is a fact about Mars that tends to be underappreciated, even by people who follow space news closely. Mars has gravity, not Earth's gravity. Mars has approximately 38% of Earth's surface gravity, meaning that a person who weighs 70 kilograms on Earth would weigh roughly 27 kilograms on Mars. This feels intuitively like an advantage. Lower gravity means less physical strain. It means that the surface operations are easier, that equipment is lighter to lift, that the cardiovascular demands of physical activity are reduced. But the human body did not evolve in partial gravity. It evolved in full Earth gravity, which means every system in your body, from your cardiovascular system to your bone density maintenance to your fluid regulation, is calibrated for 1 g of acceleration. Extended periods in zero gravity aboard a spacecraft cause serious physiological deterioration. The return of gravity on Earth, or the partial gravity of Mars, creates its own set of challenges. Bones that have lost density may fracture under loads they would previously have handled without difficulty. Muscles that have atrophied may fail to perform when demanded. The cardiovascular system, which has adapted to pumping blood in zero gravity, must readapt to working against a gravitational gradient. For crew members arriving on Mars after a long transit, the first weeks on the surface may actually be among the most physically vulnerable periods of the mission. Their bodies will be in a state of significant deconditioning. The Martian gravity, lower than Earth's but meaningfully present unlike the weightlessness of the transit, will place demands on systems that have spent months adapting to weightlessness. EVA operations, which require the crew to don heavy pressurized suits, move around on an alien surface, manipulate tools and equipment, and maintain situational awareness in a dangerous environment, will be taking place precisely when the crew's physical reserves are at their lowest. And then, having adapted to 38% gravity over months on the Martian surface, they face the return journey. Another 7 to 9 months in zero gravity aboard the return spacecraft, with bodies that have now adapted first to zero gravity, then to Martian gravity, and must now readapt to zero gravity again, followed by arrival in Earth orbit or re-entry to Earth's surface, with bodies that must cope with full Earth gravity for the first time in well over a year. The cardiovascular stress of returning to Earth after a long Mars mission is expected to be extreme. Crew members may be unable to stand unassisted. They may experience orthostatic hypertension, where the blood pressure fails to maintain itself properly when standing, causing fainting. They will likely require extensive rehabilitation before they can function independently. For astronauts returning from long-duration International Space Station missions, this recovery process typically takes months, sometimes close to a year. And those astronauts were in zero gravity for 6 months or a year, not the multi-year total duration of a Mars round trip. What does recovery look like for a crew that has been away for 3 years? The honest answer is that we don't know. We don't have data from anyone who has been through anything comparable. There is one more dimension to the return question that belongs here. Among all the physics and biology and engineering, and it is the dimension that is perhaps hardest to quantify, but impossible to ignore. What does it do to a human being to know they may not come home? The psychology literature on extreme exploration decisions is extensive, but necessarily incomplete. We have accounts from people who have chosen extremely dangerous expeditions, who have made peace with significant risk, who have found ways to hold the possibility of death or permanent separation from home without being incapacitated by it. The history of exploration is full of people who went knowing they might not return and went anyway. But there is a difference between facing the risk of not returning and making a deliberate choice to go somewhere. You will likely never leave. The early Mars missions, in the most serious scenarios being contemplated, may involve exactly that choice. Not because the people planning them are indifferent to their crews, but because the alternative, building the full return architecture for every early mission, may make those missions so expensive, so heavy, so complex, that they don't happen at all. Robert Zubrin, one of the most serious Mars mission architects of the past 3 decades, has written and spoken extensively about what he calls the case for Mars. His Mars Direct mission architecture, developed in the early 1990s, and still highly influential in Mars mission design thinking today, specifically calculates that by using Martian resources for propellant production, the return from Mars becomes achievable in a way that doesn't require launching the full return propellant from Earth. But even Zubrin acknowledges that early Mars missions involve accepting a level of risk that is fundamentally different from other phases of space exploration. He compares it to the early explorers who crossed the oceans, who went knowing that the chances of dying on the voyage were significant, that the ships of the time were unreliable, that the maps were wrong or incomplete, that the destinations were unknown and potentially more dangerous than the sea crossing. Those explorers went anyway, not because they were reckless, because they understood that some things are worth the risk, that the alternative, staying home, had its own costs, that the journey, even one that didn't lead home, could change the world. The first humans on Mars will face that same mathematics, and for some of them, the answer will be yes. Yes to going, yes to the radiation and the isolation and the dust storms and the communication delays. Yes to the gravity transition and the physical deterioration and the psychological frontier. Yes to the ascent vehicle that may or may not be waiting for them. And yes, perhaps, to staying. Not as a failure, not as a tragedy, but as a beginning. It would be easy at this point to step back from all the physics and the biology and the mission architecture and conclude that the return problem is simply one more challenge to be engineered around, that with enough money, enough technology, enough time, the obstacles will yield, as obstacles in the history of human exploration have always eventually yielded. That conclusion is not wrong, not entirely. But it misses something important about the nature of the specific obstacles involved in returning from Mars. Each individual challenge we have explored in the first part of this documentary is real and significant. The radiation, the physiological deterioration, psychological isolation, the orbital mechanics, the ascent vehicle reliability, the distance that turns communication into correspondence. But the deeper reality is that these challenges do not exist independently. They compound. A crew that has spent 7 months in zero gravity, absorbing radiation, managing the psychological friction of confinement, arrives on Mars in a state of physical and cognitive diminishment. The surface mission then places them in a high-demand environment for over a year, under continuous low-level physical and psychological stress. The radiation exposure continues. The body continues adapting to a gravity level it was not designed for. The isolation deepens rather than easing. By the time the return launch window arrives, the crew has been changed, not in the ways that motivated speakers describe when they talk about how great challenges transform us. Changed in measurable, physiological terms. Changed in their bone density, changed potentially in their vision. Changed in their immune function and their gut microbiome, and possibly, if the animal models are any guide, in aspects of their cognitive processing. And now they must perform one of the most demanding sequences in all of human spaceflight. Launch from the Martian surface. Rendezvous with the return vehicle in Mars orbit. Execute a multi-month transit back to Earth. Navigate re-entry. With bodies that have been running at the edge of their physiological capacity for years. With minds that have been isolated from Earth-based support for the same period. With equipment that has been operating in one of the most equipment-hostile environments in the solar system. For a duration that pushes the design limits of every component. This is not pessimism. This is the system thinking that serious mission architects do when they close the door and talk honestly about what the numbers show. And what the numbers show is that the margin between a successful return and a failed one is thinner than the popular excitement about Mars exploration tends to acknowledge. The first humans on Mars are not going to be tourists. They are not going to be researchers who leave when their study is done. They are going to be pioneers in the deepest and most demanding sense of that word. Some of them will return. Perhaps some of them may not have the option, and some of them may choose. When they arrive at that red horizon for the first time, when they feel the weight of a world beneath their feet that no human foot has ever touched, when they look up at the star that is Earth and feel the extraordinary remoteness of everything they have known, some of them may choose to stay, not because they gave up on home, but because they found one. Before we go further into the science, before we follow the engineering arguments to their conclusions, before we examine what Mars settlement actually means, for the long arc of human civilization, we need to spend a moment with something more fundamental, the human beings at the center of this story, because everything we have discussed so far, the radiation and the gravity transitions, and the dust, and the communication delays, and the launch windows and the ascent vehicles, all of it is ultimately a framework around a very simple and very human question. Who would actually go? Not in the abstract, not as a category, not as brave volunteers or pioneering explorers, or any of the other phrases that tend to appear in press releases and documentary narrations about space exploration. Who, specifically, as a human being with a family and a history and a set of fears and a favorite meal and a memory of what rain sounds like on a window, would agree to go to Mars, knowing they might never come back? The answer is more complex and more illuminating than it might first appear. When the Mars One project, a Dutch non-profit organization, announced in 2013 that it was accepting applications for a one-way Mars mission, it expected perhaps a few thousand responses from a narrow pool of extreme risk-takers and adventure seekers. It received more than 200,000 applications from engineers and teachers and doctors and students, from people in their 20s and their 40s and their 50s, from people with young children, with elderly parents, with comfortable lives, and no obvious reason to seek out the most extreme form of voluntary departure from everything they knew, from people in nearly every country on Earth. The Mars One project itself ultimately failed, for reasons that had more to do with its financing model than with the idea at its core. But those 200,000 applications said something important about human psychology that the statistics alone don't fully convey. When researchers began interviewing Mars One applicants and asking them to articulate why they wanted to go, a pattern emerged that was, in certain ways, surprising. Very few of them cited a desire for adventure in the traditional sense. Very few described themselves as thrill seekers, as people who craved danger or novelty, or the rush of the unknown. Many of them were, by their own description, fairly ordinary in their day-to-day lives. People who drove sensible cars and worried about their health insurance and called their parents on weekends. What they shared was something different, a sense that the thing they were being offered, the chance to be part of the most significant moment in human exploration since the first migrations out of Africa, was worth more than comfort, worth more than proximity to home, worth more than the ordinary continuity of a life lived on one planet. One applicant described it this way, in terms that capture something the numbers cannot. She said that she had spent most of her life feeling as though history was something that happened to other people in other times, that the Mars mission was the first thing she had ever encountered that made her feel as though she could be part of something that would genuinely matter, not just to her or to people she knew, but to every human being who would ever exist afterward. She wasn't wrong, and that sense of meaning, that willingness to exchange the familiar for the historically significant, is one of the most consistent themes in the accounts of people who seriously consider one-way Mars missions. They are not running away from Earth. They are running towards something that Earth, in all its comfort and familiarity, cannot offer. The moment you take seriously the possibility that early Mars missions might involve people who don't return, a set of ethical questions emerges that space agencies and mission planners have generally preferred not to discuss publicly. And those questions deserve to be examined directly, because the way we answer them will shape not just the first Mars mission, but the entire subsequent relationship between humanity and the rest of the solar system. The first question is consent. In the history of human exploration, the ethics of consent have been complicated. Early ocean voyagers and polar explorers operated in a world where the full nature of the risks they were accepting was often unknown to anyone, including themselves. They consented to a journey, not to a specific outcome, because the specific outcomes were not yet mappable. A Mars mission is different. We know in considerable detail what the risks are. The radiation exposure can be calculated with reasonable precision. The physiological consequences of long-duration spaceflight are documented. The engineering challenges of ascent from Mars are understood. The communication constraints are fixed by the laws of physics. If a crew member agrees to a Mars mission with full knowledge of all of this, understanding that return is possible but not guaranteed, that the probability of surviving the entire round trip is meaningfully less than certainty, is that consent valid? Most ethicists who have engaged seriously with this question say yes, with conditions. The conditions center on the quality and completeness of the information provided, on the freedom from external pressure in making the decision, and on the ongoing ability to change one's mind up until the point where changing one's mind becomes physically impossible. That last condition is where things become genuinely complicated. There is a moment in every Mars mission, somewhere in the transit toward Mars, when turning back becomes more expensive in fuel and in risk than continuing forward. A point of no return, in a practical engineering sense. Before that point, the mission can be aborted and the crew return to Earth, though not without cost and risk. After that point, continuing to Mars is the safer option. Once on the Martian surface, for the duration between arrival and the next return window, there is no point of return at all. The crew is there. They stay until the window opens. What happens if, after arriving on Mars, after the reality of the situation has replaced the abstraction of the planning, someone no longer consents, not in a dramatic crisis of faith way, but in the quieter and more human way that any person might find that what they agreed to in the theory is different from what they are living in practice. This is not a hypothetical designed to undermine the case for Mars exploration. It is a genuine ethical challenge that mission planners will need to address before they put human beings on a spacecraft pointed at another planet. The second ethical question is harder. If some Mars missions are designed from the beginning as one way, or likely one way, who bears responsibility for the selection of the people who go? In military history, The ethics of sending people into situations where survival is unlikely has been the subject of centuries of moral philosophy. The general consensus is that such decisions can be ethically justified under specific conditions. Genuine necessity, proportionality of the expected outcome to the cost, exhaustion of alternatives, and the fullest possible voluntary participation of those who take the risk. Does Mars settlement meet these conditions? The argument that it does goes something like this. The long-term survival of Earth's biosphere is not guaranteed. Extinction-level events, whether from asteroid impacts, climate change, supervolcanic eruptions, or other catastrophic possibilities, represent a genuine existential risk to the only form of life we know exists in the universe. A multi-planetary civilization is, in the most fundamental sense, a hedge against extinction. The people who go to Mars and stay, even if they can never return, are protecting not just humanity's future, but the future of all life that has emerged from this planet over 4 billion years. That is a large claim, but it is not an irrational one. And it is the argument that serious Mars advocates, from Elon Musk to Robert Zubrin, to the researchers and engineers who have spent careers thinking about what it would take to become a multi-planetary species, return to again and again. The third question is perhaps the most intimate. What do we owe the families of the people who go? A Mars mission is not just a mission for its crew. Every person on that spacecraft carries with them a network of relationships, of obligations, of love, that does not simply pause for the duration of the mission. Parents who will age and may die while their child is unreachable in any meaningful way. Partners who will manage life alone, or not alone, through years of waiting. Children who will grow up writing messages to a parent that take up to 22 minutes to arrive, and require the same time to receive a reply. The International Space Station has normalized, to some degree, the experience of having a family member in space. Astronauts on 6-month missions maintain regular video calls with their families, participate in birthday celebrations from orbit, watch their children grow through screens. The connection is imperfect but real. Earth is visible from the station window, close enough to feel present. For Mars, the experience is categorically different. The communication delay alone fundamentally changes the texture of long-distance connection. A video call, in the traditional sense, is impossible when the lag is measured in minutes. What replaces it is something more like an extended correspondence. Video messages recorded and sent, received and replied to, with hours or days between exchanges. This is something to be said for this form of communication. Letters have always had a depth, a deliberateness, that real-time conversation sometimes lacks. The necessity of saying what you mean completely, without the possibility of immediate clarification, can produce a kind of eloquence that spontaneous conversation doesn't always achieve. But it is not the same as being there. It is not the same as being present for the ordinary moments that make up a life. The school performances and the illnesses and the arguments resolved over dinner, and the evenings where nothing of consequence happens but the simple fact of being together. Researchers who have studied the families of Antarctic expeditioners and long-duration submarine crew members have documented the psychological costs of extended absence on the people left behind. Elevated stress, increased rates of depression, relationship strain that sometimes survives the return and sometimes does not. For the families of Mars crew members, These costs will be amplified by duration, by distance, and by uncertainty. And for the families of crew members who may not return, the cost is of a different order entirely. This is not a reason to abandon the project. Human beings have always been willing to make sacrifices in pursuit of things larger than themselves. The families of great explorers, of soldiers in just wars, of scientists who gave their health and sometimes their lives to understanding the world, have always paid a portion of the cost of those extraordinary commitments. But it is a cost that belongs in the conversation, not in the footnotes. The first humans who go to Mars will not be going alone, in the full sense. They will be taking the love and worry and sacrifice of everyone who matters to them along with them, carried not in their luggage, but in whatever that irreducible thing is that connects human beings to each other across any distance, even a distance measured in light minutes, even a distance that may never be crossed again. Let us now shift our perspective, not inward, toward the individual stories of courage and sacrifice and chosen loss, outward, toward what happens after the first people arrive, after the habitat is established and the experiments are running, and the initial crisis of arrival has settled into the difficult routine of survival. After the crew has been on Mars for a year, and then 2 years, and then perhaps longer. After the question of whether they are coming home has been answered, one way or another, because something extraordinary begins to happen when a group of human beings stops asking how they will get back to where they came from, and starts asking how they will build something where they are. The transition from survival to settlement is not a single moment. It is a gradual shift in the way a group of people relates to their environment. In the early phases of the mission, every resource, every calorie, every cubic meter of pressurized atmosphere, every component of every system exists in relation to the mission. The mission has goals, timelines, objectives set by people on Earth, return conditions, success criteria. But if the crew is staying, or if they come to understand that staying is the most probable outcome, the relationship between the people and the place begins to change. Anthropologists and historians who have studied the early phases of human settlement in genuinely novel environments, from the first communities in the Americas to the settlement of remote Pacific islands, to the establishment of communities in Antarctica, describe a common pattern. The moment when a group stops thinking of themselves as travelers who are somewhere temporarily and starts thinking of themselves as people who live somewhere is the moment when genuine civilization begins. It is the moment when they start planting things they don't expect to harvest themselves, when they start building structures intended to outlast them, when they start thinking about the children who might be born there, and what those children will need, and what kind of world they are creating for them. On Mars, this transition will be complex and emotionally fraught and practically complicated in ways that have no precedent. But it will happen, and when it does, the question of return will begin to look different than it does at the beginning of the mission. Not as a failure avoided or a tragedy accepted, but as a choice made in full knowledge of what it means. Humans have always made places their own. It is perhaps the most consistent thread in our entire evolutionary and cultural history. We arrived in environments that were cold and dark and dangerous and poorly suited to the body's evolution had given us. And we built fires and shelters and communities, and eventually cities. We transformed hostile places into home, not by waiting for the environment to welcome us, but by imposing our own insistence on belonging. Mars will not welcome the first humans who arrive there. It will be indifferent to them in the way that all of the physical universe is indifferent to the desires of living things. It will not offer breathable air or comfortable temperatures or soil that grows food or water in convenient liquid form. It will offer rock and dust and radiation and cold and a thin, poisonous atmosphere. And humans will begin with the tools they bring and the ingenuity they carry and the extraordinary capacity for adaptation that 4 billion years of evolution has built into every cell of their bodies to make it home. The word terraforming has a science fiction quality to it, a sense of the grandiose and the impossibly distant that sometimes makes serious scientists reluctant to engage with it in public forums. But the concept itself is not science fiction. It is applied planetary science. And the question of whether Mars can be made more Earth-like, not necessarily in a human lifetime, or even in many human lifetimes, but on timescales that human civilization has shown itself capable of working toward, is one that serious researchers have studied in considerable depth. Mars was not always the frozen, thin-aired desert it is today. 4 billion years ago, in the earliest period of the solar system, Mars had something that it has now almost entirely lost: a substantial atmosphere, liquid water at the surface, possibly even a global magnetic field, geological evidence in the form of ancient riverbeds, lake basins and mineral deposits that can only form in the presence of liquid water, tells us that Mars once had conditions that, by Earth's standards, would not have been entirely hostile to life. What happened? The answer is connected to the absence of that global magnetic field. Earth's magnetic field is generated by the motion of molten iron at its outer core, a dynamo driven by the heat of Earth's interior. This field extends far into space and deflects the solar wind, protecting the atmosphere from being stripped away particle by particle over billions of years. Mars lost its magnetic field early in its history, likely because its smaller size meant its interior cooled more rapidly, shutting down the dynamo that would have sustained the field. Without that protection, the solar wind gradually eroded Mars's early thick atmosphere. Atmospheric pressure dropped. Temperatures fell. Water that had existed at the surface either evaporated into space or froze underground, where it remains today as ice, vast reserves of it, locked in the polar caps and beneath the surface in permafrost. This history is significant because it tells us what Mars is capable of in principle. It was once a world with an atmosphere and liquid water. It could, in principle, become that again, though what that would require is staggering in its scope. The most commonly discussed approaches to Martian terraforming involve raising the atmospheric pressure and temperature enough to allow liquid water to exist at the surface and to make the environment progressively less hostile to life, if not immediately to unprotected human beings. This might involve releasing greenhouse gases, perhaps from industrial processes or from warming the Martian poles to release trapped carbon dioxide, potentially importing ammonia from the outer solar system. And over very long timescales, managing the atmosphere's evolution towards something more breathable. Carl Sagan was among the first scientists to seriously propose Martian terraforming in a 1973 paper that considered the possibility of warming Mars by introducing photosynthetic organisms into the polar caps. The idea was speculative then and remains speculative now, but it established an important principle. Terraforming is not magic. It is the application of planetary science on a civilizational timescale. The people who first go to Mars will not live to see a terraformed world. Their children will not. Their grandchildren will not. The timescales involved in meaningfully altering a planet's atmosphere run to thousands or tens of thousands of years, even in the most optimistic projections, and more realistically to much longer. But civilizations think on long timescales when they believe in their own continuity. The medieval cathedrals of Europe were built by people who knew they would never see them completed. Ancient irrigation systems in Mesopotamia and China and Peru were constructed by communities that understood the full benefit would only accrue to generations not yet born. The planting of slow-growing forests has always been an act of faith in the future. If human beings establish a permanent presence on Mars, they will begin from the very first day. A project that has no end date. A slow transformation of a world. A commitment made not just to themselves, but to every human being who will ever live on that planet. Thousands of years from now, who will breathe air that has been made progressively more breathable by the accumulated work of all the generations who came before them. The first humans on Mars, the ones who don't come back, are not just explorers. They are the first chapter of an entirely new book of human history. There is a quieter dimension to the return question, one that emerges not from the engineering or the biology or the ethics, but from the simple human experience of being somewhere utterly unlike anywhere you have ever been. People who have spent time in genuinely remote environments, who have lived for months in Antarctica, or on research vessels in the middle of the Pacific, or in underground cave systems during long scientific expeditions, often describe a psychological phenomenon that is difficult to articulate but consistently reported, a shift in the sense of what is normal. After enough time in an alien environment, the environment stops feeling alien. The routines you establish, the rhythms of your days, the familiar faces and voices of the people around you, the particular quality of the light, and the way sound behaves in your specific space. All of it gradually becomes the baseline, becomes what the mind expects, becomes home in the functional sense, even when it is nothing like home in the emotional sense. For Mars crew members on a long surface mission, this shift will happen. The thin copper light of a Martian dawn, filtered through an atmosphere carrying dust, that makes the sky a different color than any sky on Earth, will become what their eyes expect in the morning. The particular rhythm of the habitat, the sounds of the life support systems, the view from the windows, the texture of the days, will become familiar in the way that all human environments eventually become familiar to the people who inhabit them. And something else will happen. The Earth, the planet they came from, the world that contains everything they have ever known except the people in this habitat and the mission they are living, will become abstract in the way that all things become abstract, when you can't see them and can't touch them and can only reach them through delayed messages that arrive like letters from a world you used to live in. This is not a pathology. It is a feature of human psychology that has allowed us to survive every environment we have ever settled in. The ability to make the present real and the absent manageable. The capacity to invest in the world around you rather than spending all your energy grieving the world you left. But for the question of return, it has consequences. Astronauts returning from long International Space Station Missions consistently describe a period of what they call readaptation to Earth that goes beyond the physical. They describe feeling, for weeks or months after return, slightly out of place. As though Earth, the world they spent their whole lives in, has become slightly unfamiliar while they were gone. For a crew that has spent 2 or 3 years on Mars, this disorientation upon return, if return happens, will be of an entirely different magnitude. And for a crew that doesn't return, the psychological journey goes in the other direction. Mars becomes real. Earth becomes the memory, not immediately, not easily, not without grief and loss, and the particular kind of homesickness that has no remedy, because the home in question is a world rather than a house. But eventually, and in that eventual settling into Martian reality, something new will emerge. Something that has no precedent in human history. The first people, for whom Mars is simply where they live. The idea of going somewhere with no certain path of return is not new. It is, in a meaningful sense, the story of almost every major human migration in history. The first human beings who crossed the land bridge from Asia to the Americas, tens of thousands of years ago, were not making a round trip. They were following game, or fleeing competition, or driven by whatever complex mixture of necessity and curiosity and chance has always propelled human movement across the earth. They did not know what was on the other side. They had no way to know whether they could return. Many of them couldn't. They went anyway. The Polynesian navigators who crossed the Pacific in open canoes, reading the stars and the currents and the flight patterns of birds. Settling islands, separated by thousands of miles of open ocean, were not operating with a guaranteed return route. Some of them found new islands and settled them. Some of them found open ocean and never came back. The ones who found the islands built civilizations that lasted for centuries. The colonists who left Europe for the Americas, for Australia, for every corner of the world that European expansion touched. Many of them went knowing that return was unlikely. The cost of the voyage, the uncertainty of the new world, the economic and social conditions that made going preferable to staying, meant that for many of them, the ship that carried them away from their home continent was a one-way vessel in everything but name. Some of those migrations were coerced. Some were desperate. Some were motivated by greed or ambition, or the particular cruelty that sometimes drives human expansion into new territories. But some of them were motivated by something more fundamental. The human drive to see what is on the other side of the horizon, to find out what happens in the places where the maps say only unknown, to be in whatever small or large way part of the expanding edge of human experience. Mars is the next horizon. It is not the moon, close enough to feel like a neighbor. It is not a space station, orbital and temporary by design. It is another world. A world with its own geology and its own climate and its own history, stretching back 4.5 billion years. A world where the sunrises are different, and the gravity is different, and the sky is a different color, and the ground beneath your feet has never once in the history of the universe felt the weight of a living thing before you stepped on it. Going there and not coming back is not a failure of technology or ambition. It is the latest chapter in a story that began when the first human beings stood on the shore of a large body of water and wondered what was on the other side, and decided to find out. Here is the question that tends to stop conversations about Mars settlement in their tracks. More than the radiation and more than the ascent vehicles, and more than any of the engineering challenges we have discussed. What about children? If the first humans on Mars stay, if a settlement grows, if Mars becomes something more than a temporary research outpost, then eventually, inevitably, the question of reproduction on Mars will move from theoretical to practical. No human being has ever been born anywhere except Earth. We do not know what pregnancy looks like in 38% gravity. We do not know how fetal development proceeds in an environment where cosmic radiation is a constant presence rather than an occasional elevated risk. We do not know how human physiology adapts across generations to a gravitational environment that is substantially different from the one in which human biology evolved. These are not questions with answers in the current scientific literature, because there has never been an opportunity to study them. The ethical constraints around reproductive research in space are significant and appropriate, and the practical constraints are equally real. What we do know from our understanding of human developmental biology is that early development is exquisitely sensitive to environmental conditions. Gravity plays a role in the development of the inner ear, in the orientation of cells during early embryonic development, in the formation of the skeletal system. Whether these processes function normally in Martian gravity is genuinely unknown. Some researchers have suggested that children born on Mars might develop differently from their Earth-born counterparts, in ways that could make them better adapted to their world, but potentially less able to live on Earth. Different bone density, different cardiovascular systems, different musculature, a body shaped by Martian gravity rather than Earth's. The irony of this possibility is profound. The first generation of humans born on Mars, if things go that way, might be the first humans in history for whom the return to Earth is not just impractical, but physiologically difficult. Not because of the journey, but because their bodies were shaped by a different world. In that sense, the question of whether the first humans on Mars will never come back might have an answer that is stranger than any of the engineering scenarios we have discussed. It might be that the humans who truly cannot return are not the first ones who arrive. They are the ones who are born there, the first Martians, children who will grow up looking at a bright star in the Martian sky, knowing it is Earth, knowing it is where their parents or grandparents came from, knowing it is the origin point of their species, but for whom it is not home, for whom Mars is home. We have spent this documentary exploring the many reasons why returning from Mars is difficult, why it may be unlikely for some missions, why it may be impossible for others, why some people will choose not to return even when return is possible. But now we need to consider the other side, because some people will return. Not all of the first humans on Mars will stay. Mission architectures that include return capability will presumably eventually succeed. Crew members who complete their surface missions and make it back to the ascent vehicle and rendezvous with the Earth return vehicle and survive the transit home and land safely on Earth will exist, and what they bring back will be extraordinary. Not just scientific data, not just geological samples and atmospheric measurements and biological findings. All of those things will be valuable beyond measure. What they will bring back is something that has always been the most important cargo carried by explorers returning from distant places: experience, the knowledge of what Mars is actually like. Not the models, not the situations, not the projections from orbital observations and rover data, but the felt, embodied knowledge of people who stood there and breathed recycled air and watched Martian dust accumulate on their habitat windows and felt the lower gravity in their muscles and survived the isolation and did the work. That knowledge will transform how we understand what Mars settlement requires. It will reveal which of our models were right and which were wrong. It will expose the unexpected challenges that no amount of pre-mission analysis could have predicted. And it will show us, in the direct testimony of people who lived through it, what human beings are actually capable of in that environment. Every great era of exploration has been shaped by the accounts of the people who went and came back and told what they found. Columbus's voyages changed the map of the world. Cook's explorations transformed European understanding of the Pacific. The accounts of Antarctic expeditions in the early 20th century built the scientific foundation for everything that followed in polar research. The first humans to return from Mars will carry within them a transformation that no words can fully convey, but that will inevitably reshape our understanding of what it means to be human in the solar system. They will have been somewhere that no human being had ever been before. They will have survived things that had never been survived before. They will have looked at Earth from the surface of another world, seen it as a point of light, felt the reality of their cosmic situation in a way that even astronauts orbiting Earth cannot fully experience. And they will come home changed in ways that will take years to fully understand. Some of them will speak publicly about what they experienced and inspire the next generation of explorers. Some will become researchers, helping to analyze the data they collected and design the next missions based on what they learned. Some will quietly resume their lives, carrying within them something that cannot be shared completely because it cannot be fully translated into the experience of someone who was not there. All of them will have proved something that needed proving, that human beings can go to Mars and come back. And that knowledge will change everything about the trajectory of what comes next. There is one more dimension to the return question that belongs in this story, and it is perhaps the most important one. It is the dimension of what happens to the project of Mars exploration as technology improves. The challenges we have discussed throughout this documentary are real and significant. The radiation, the physiological deterioration, the ascent vehicle reliability, the communication delays, the orbital mechanics, the psychology of extreme isolation, but none of them are permanent features of the landscape of human capability. They are problems as they exist right now, with the technology and the knowledge and the resources that exist right now. And the history of human technology is a history of solving exactly this kind of problem. 40 years before the Apollo program, the idea of landing human beings on the moon would have seemed not merely ambitious, but frankly, delusional to most serious scientists. The technology did not exist. The knowledge did not exist. The engineering frameworks for thinking about the problem were barely in their infancy. The gap between the first airplane flight in 1903 and the first moon landing in 1969 is 66 years. 66 years from a wooden and fabric aircraft that flew for 12 seconds to a spacecraft that carried human beings to another world and returned them safely. In the context of that trajectory, the specific challenges of returning from Mars are not impossible barriers. They are engineering problems waiting for solutions that are not yet developed. Radiation shielding technology is advancing. Better materials, active magnetic shielding systems, pharmaceutical approaches to radiation protection, and faster transit times made possible by improved propulsion systems could all reduce the radiation dose received on a Mars mission substantially. Nuclear propulsion systems that have been in development in various forms since the 1960s could cut transit times significantly, reducing total exposure. Medical technology for managing the physiological consequences of long-duration spaceflight is advancing. Countermeasures for bone loss, muscle atrophy, and cardiovascular deconditioning are improving with every mission. Pharmaceutical approaches to some of the problems are in development. Better understanding of the specific challenges leads to better solutions. Ascent vehicle technology and reliability will improve as we gain experience landing on Mars and operating equipment there. The first missions will face uncertainties that later missions will not, simply because later missions will have the experience of earlier missions to draw on. Communication technology cannot change the speed of light, but it can change how effectively humans operate under communication delay. Better artificial intelligence systems, more autonomous habitat management, improved decision support tools, all of these will make the isolation of the communication delay more manageable for future crews. The point is not that all problems are solvable on any particular timeline. The point is that the picture of Mars return capability will look substantially different in 20 years, or 30 years, or 50 years, than it does today. The first humans to go to Mars will face the most challenging version of every problem. They will go with the least capable technology, the least experience, the least infrastructure, and the least developed medical and engineering understanding of the specific challenges they face. Every subsequent mission will face a slightly easier version of those challenges, until, at some point, that we cannot precisely locate, but can reasonably anticipate. Returning from Mars will not be the existential question it is for the first missions. It will be the expectation. We have traveled far in this documentary, from the orbital mechanics that govern launch windows to the biology of the human body in space, from the psychology of extreme isolation to the ethics of one-way missions, from the engineering of ascent vehicles to the possibility of children born on another world, from the history of human migration to the future of planetary civilization. All of it circles back to the question we began with. Why won't the first humans on Mars come back? And now, having explored the territory, we can answer it with more precision than the title suggests. Some of them won't come back because the technology of the first missions may not support reliable return. The ascent vehicles, the return propellant, the spacecraft, all of it is being developed at the frontier of human engineering capability, and frontiers are the places where things go wrong in ways that could not be fully anticipated. Some of them won't come back because their bodies, transformed by the journey and the surface mission and the radiation exposure, may not be able to survive another transit and the return to Earth. Gravity. The cumulative physical cost of the round trip may, for some individuals, be too high. Some of them won't come back because they choose not to, because they arrive on Mars and find something there that they did not expect to find. Not the absence of home, but the presence of meaning, the extraordinary, irreplaceable significance of being one of the first human beings to stand on another world. to contribute to the first permanent human presence in the solar system, to be part of the beginning of something that will unfold over centuries and millennia. Some of them will look at the bright star that is Earth and feel something that explorers throughout history have felt when they reached the edge of the known world and realized they were not going back, not despair, not resignation. Something closer to clarity. The understanding that they are exactly where they are supposed to be. That the thing they came to do is not a visit. It is a beginning. Mars is not the end of this story. It is the beginning of one. If human beings establish a permanent presence on Mars, if they survive the challenges and solve the engineering problems and navigate the ethics and build something that lasts, the implications extend far beyond the red planet. Mars would be the first proof of concept that humanity can sustain a civilization beyond Earth. Not the Moon, which is close enough to be a satellite of Earth in most practical senses. Mars. A genuinely separate world with its own independent life support systems, its own food production, its own culture beginning to differentiate from Earth's in ways that no one can fully predict, but that history suggests will be profound and irreversible. From that first proof of concept, everything else in the solar system opens up. The asteroid belt, with its extraordinary mineral wealth, the moons of Jupiter and Saturn, some of which are now known to harbor liquid water oceans beneath their icy surfaces, environments that may be among the most promising places in the solar system to look for life. The outer planets, mysterious and enormous, their atmospheres and their systems of moons barely explored. And beyond all of that, the interstellar horizon, impossibly distant by current technology, but not impossible in principle. Not impossible if the trajectory of human capability continues in the direction it has always gone. None of that happens if the Mars project fails. None of that happens if the first missions don't go, or if they go and the people don't survive, or if the challenges of the first permanent settlement prove more than the technology and the human will of the moment can sustain. The stakes of the Mars question are not small. They are as large as the question of whether humanity remains a single-planet species, vulnerable to every catastrophe that a single planet can produce, or becomes something else, something more resilient, something more capable, something more fully alive to the possibilities of the universe it exists within. The cosmos is not waiting for humanity to feel ready. The universe has been unfolding for 13.8 billion years without particular regard for whether any living thing is prepared for the next chapter. The question is not whether we can afford to go to Mars. The question is whether we can afford not to. Imagine for a moment that it is sometime in the not impossibly distant future. A human being is standing on the surface of Mars, outside a habitat that has been home for more than a year, looking at the sky. The Martian sky at twilight is not blue. It is a faint pink, shading toward darker blue at the zenith, a sky that looks simultaneously familiar and entirely wrong. The dust in the atmosphere catches the light differently than Earth's atmosphere does, producing colors that have no exact analog in any Earth landscape. And in that sky, but bright enough to cast the faintest shadow on a moonless night on Earth, is a star. This person knows what that star is. They know that on that star, on that world suspended in the sky above them, every human being who has ever lived except the small crew in this habitat was born. They know that everything familiar to them, every landscape they grew up in, every person they love, every book they read, and piece of music they heard, and meal they remember, exists on that world, that their entire past is contained in it, compressed by distance into a single point of light. And they know with a certainty that no training or briefing fully prepared them for, that they will not be standing on that world again. Perhaps ever. Perhaps not for years. Perhaps for the rest of their life. What they feel in that moment, no documentary can fully convey. No simulation or analog environment, or Mars One application or carefully worded mission architecture document has managed to capture it, because it has not happened yet. We are still on this side of that moment. It exists ahead of us, somewhere in a future that is approaching at the speed of 1 second per second. But we can say something about what they will carry with them into that moment. They will carry the knowledge that human beings have always stood at the edge of the known world and looked out at the unknown with exactly this mixture of grief and wonder and terrifying aliveness, that the explorers of every era who stood at the boundaries of their maps and chose to go further were not exceptional in being fearless. They were exceptional in going despite their fear. They will carry the understanding that what they are part of is not just a mission or a scientific program or a geopolitical achievement. It is the continuation of something that began the moment the first living things on Earth developed the capacity to move toward things that were unfamiliar. That 4 billion years of evolution and 10,000 years of human civilization have been building in some strange and roundabout way toward this, and they will carry, somewhere underneath everything else, a hope. Not the shallow hope that things will work out easily. Things will not work out easily. Mars is not easy. Nothing about what they have undertaken is easy. But a deeper hope, the kind that doesn't require guarantees, the kind that exists independently of outcomes and timelines and mission success metrics, the hope that comes from being exactly where your deepest nature calls you to be, the hope that comes from having chosen, in the fullest possible awareness of what you were choosing, to go. The title of this documentary is not quite a prediction. It is not a claim that no first humans on Mars will ever return. History is too full of achieved impossibilities for that kind of certainty to be credible. It is, instead, an invitation to take seriously something that the excitement of Mars exploration sometimes glosses over. That going to Mars is not like going anywhere else that human beings have ever gone. That the challenges of return are real and significant and not simply engineering problems awaiting straightforward solutions. That some of the people who go to Mars will face the genuine possibility, and perhaps the reality, that they are going somewhere they will not leave, and that this fact, uncomfortable as it is, belongs at the center of our thinking about Mars, not in the fine print. Because how we think about the return question shapes everything. It shapes how we design the missions. Whether we invest in return architecture or surface infrastructure. Whether we select crews for short-term operational excellence or long-term adaptability. Whether we think of Mars as a place to visit or a place to inhabit. It shapes how we think about the ethics. Who goes, what they are told, what we owe them and their families, what kind of civilization we are demonstrating ourselves to be in how we make these decisions. And it shapes how we understand the project of human exploration itself. If we go to Mars thinking only about how to get people there and back as quickly as possible, we are thinking about Mars as a destination, a place to go and leave, If we go thinking about how to build something that lasts, something that can eventually be self-sustaining, something that plants the first root of a genuinely multi-planetary human civilization, we are thinking about Mars as a beginning. The difference between those two orientations is not technical. It is philosophical. It is about what kind of species we want to be. The universe around us is vast beyond any scale that human intuition was built to comprehend. The galaxy contains hundreds of billions of stars. The observable universe contains hundreds of billions of galaxies. The sheer scale of what exists beyond the thin shell of atmosphere that has contained all of human history is genuinely incomprehensible. Not in the loose sense in which that word is often used, but in the strict and literal sense. We cannot comprehend it, but we can reach toward it. We can take the first step, which is the hardest step, which is always the step that requires you to leave the safety of what you know and move towards something that is not yet real, but that you can see in the mind's eye, across the distance, waiting. The first humans on Mars may not come back, and in their staying, in their survival, in their slow and difficult transformation of an alien world into something approaching home, they will change what it means to be human in a way that reaches forward into a future we cannot yet see. They will be the ancestors, not the visitors, the ones who went and stayed so that everything that came after could happen. And 1,000 years from now, in a city under a dome on Mars, or in an open-air settlement, breathing an atmosphere made thicker by centuries of slow work, someone will look up at a star, a blue-white star, bright enough to read by on the darkest nights, and they will know what it is, and they will know what was given up, and what was chosen, and what was built in the space between that world and this one, by the first humans who went to Mars and never came back.